Welcome to Biogas Basics. My name is Jürgen Kuber, and this is the third and final part about the mass balance of a biogas plant. This presentation will deal with the impact of kinetics and residence time. In previous calculations, we kept the biogas yields constant. A feedstock would make the same amount of biogas, regardless of the digester size. With previous models, we could not answer the question, what if we make the digester 20% larger? How much more biogas will we produce? Instead, the assumption was that the digesters were large enough, so that an increase or decrease of digestion volume will not lead to a significant change in the biogas yield. In this presentation, we will calculate a dynamic mass balance that takes degradation kinetics into account. It will respond to a change of digester size with a change of biogas yield. In previous mass balances, we have worked with known biogas yields. In this presentation, we are introducing biogas potentials and conversion factors. The biogas yield is the biogas potential times the conversion factor. The biogas potential is the biogas yield if the digester has infinite size, or in a batch test, if the batch would run for an infinite time. The biogas yield is the amount of biogas produced per mass substrate used in a particular digester. It will vary with digester size, though there will be a law of diminishing returns. Doubling the digester size will not double the biogas yield. Instead, the amount of undigested substrate leaving the digester with the effluent will roughly halve. The ratio of biogas yield and biogas potential is the conversion factor, and it will approach 1 for very large digester sizes. We will also introduce a new species, substrate. Substrate is the part of organic dry matter that can be converted into biogas. We ignore biomass buildup in this presentation. Feedstock comprises different fractions that degrade with different reaction rates. Soluble sugars convert quicker than starch, or soluble hemicellulose, which converts faster than insoluble lignocellulose. For the purpose of the mass balance, we lump the different substrates into 3 fractions: a rapidly degrading fraction, a medium-fast degrading fraction, and a slowly degradable fraction. Rapidly degradable substrates are glycerol, sugar solutions, volatile fatty acids, or other water-soluble liquids containing carbon and hydrogen. The medium-fast degradable fraction is starch, hemicellulose, proteins, or other water-soluble biopolymers. The slowly degradable fraction is lignocellulose, which is insoluble cellulose covered with undegradable lignin. For example, straw is 90% lignocellulose, so slowly degradable fraction and 10% medium-fast degradable fraction. Grass is 40% hemicellulose and protein and 60% lignocellulose. Sugar beet pulp is 100% pectin, medium-fast degradable. Sugar beets are 2/3 saccharose, rapidly degradable, and 1/3 pectin, medium-fast degradable. For unknown feedstocks, a fodder analysis can give some insights into the composition. I have a whole mini-series about the growth of microorganisms, where I discuss different kinetics and when to use them. In this presentation, I will only use first-order kinetics, which are the most relevant when the hydrolysis kinetics are the limiting step of the biogas process. We allocate a first-order kinetic constant to each of the 3 fractions, typically 1 day to the power of -1 or higher for the rapidly degradable fraction, 0.4 day to the power of -1 for the medium-fast degradable fraction, and 0.07 day to the power of -1 for the slowly degradable fraction. The conversion factor must be calculated for each digestion stage and every substrate fraction individually. It depends on the residence time of the respective digester and kinetic constant of the respective fraction. The product of reaction constant and residence time is the first-order Damköhler number. The conversion fraction is calculated with the steady-state CSTR formula. The biogas production in each stage is then calculated by balancing the 3 substrate fractions. This will make the biogas yield dynamic. It is no longer fixed, as in previous examples. For a known residence time in the digester, we can now calculate the conversion factor for each substrate fraction, and because we know the composition of the feedstock, we can calculate the conversion factor for the digester. These curves show the substrate conversion factor as a function of hydraulic residence time for 3 different kinetic constants. The green line is for small molecules, the rapidly degradable fraction. Effectively, these molecules are consumed instantly and completely when fed into a digester. In the mass balance, we will assume that these molecules degrade to 100%, making a kinetic model irrelevant. The reaction constant is very high. How high does not matter. The orange line shows the conversion efficiency for a medium-fast degradable molecule, for example for soluble polymers. The deciding parameter for designing biogas reactors for fibrous material is the conversion kinetic of the lignocellulose. Even in reactors with high residence times of 40 to 50 days, the conversion is nowhere near complete. Here's an overview of the balancing algorithm. Because the yields are not known, we do not know the final conversion rate and dilution requirements. We have to use iteration to calculate the solution. The following algorithm is very stable and converges quickly to the feasible solution. First, we estimate the residence times of each step and the composition of the process water. A first estimate of the process water composition can be obtained by balancing the whole plant, i.e. feedstock in and biogas, solid and liquid digestate out. The liquid digestate composition is the first estimate of the process water composition. Then, we calculate the conversion efficiencies for each substrate fraction in each stage. The effluent of the last stage is separated into solid and liquid digestate. The composition of the liquid digestate is the new estimate for the process water composition. We also update the residence times of each stage with the respective effluent streams taken from the mass balance. We repeat the iteration loop a couple times until the results for residence times and process water composition no longer change, at which point we have reached the solution. Before we start with the mass balance, let's briefly discuss substrate. Earlier, we have defined that substrate plus water is biogas plus biomass. For the purpose of this mass balance, we ignore the biomass formation. Substrate is the part of the organic dry matter that can be converted into biogas. Not all biogas mass comes from organic dry matter. Some comes from water. This part is not covered by the substrate mass. Organic dry matter is substrate plus inert organic dry matter. We lump the different substrates into three groups: rapidly degradable, medium-fast degradable, and slowly degradable. We then use a BMP test to fit the biogas or methane production curve with a first-order kinetic. The parameter fit gives us the split, how much substrate is fraction 1, 2, or 3. Alternatively, we can use a fodder analysis to predict how much of the substrate is rapidly, medium-fast, or slowly degradable. In the separation step, we model substrate as fresh matter soluble. We will also need a new rule for calculating the process water demand for dilution. Process water contains substrate, and the substrate will be degraded in the digester, lowering the TS of the process water. This might sound complicated at the moment, but I will walk you through the Excel model of the mass balance step by step in the coming slides. Here's how we balance the substrate fractions in Excel. We start with the previous feedstock table. We extend the table with three new columns: substrate fraction 1, 2, and 3, shown as F1, F2, and F3. These fractions describe the mass percentage of biogas produced from each fraction. They add up to 100%. Maize silage consists of roughly 60% starch and 40% lignocellulose. Starch is water-soluble up to 1% and is medium-fast degradable. The lignified cellulose fraction is insoluble and degrades slowly. Microorganisms must grow on its surface and chew their way through a cellulose fiber. Cattle manure has higher levels of slowly degradable fibers, 70% here. The medium-fast degradable fraction comprises proteins and hemicellulose that haven't been degraded in the cow. Milled straw is mostly lignocellulose. I chose 80% here. The 20% medium-fast degradable fraction are from very small straw particles created in the milling process that degrade quicker. Whey permeate is lactose, a glucose-galactose double sugar. It will be converted to biogas almost instantly and completely in any commercial AAD plant. I allocate 100% of its biogas potential to fraction 1. Chicken muck is roughly a 50-50 mix of medium-fast and slowly degradable fraction comprising lots of protein and cellulose fiber from bedding. The exact split depends on the type of chicken muck and bedding material, if present. Next, we calculate the fraction 1 weight percentage of the total biogas produced by the feedstock mix. It is the sum product of fresh matter, TS, LOI, biogas potential, density, and fraction 1 divided by the total fresh matter and average, TS, LOI, biogas potential, and biogas density. In total, 1.9% of the total biogas potential stems from fraction 1, which comes exclusively from the whey permeate. We repeat the calculation for fraction 2 and 3. Roughly half of the biogas potential comes from the slowly degradable fraction 3, and the remainder, 48.2%, from fraction 2. In the next slide, we will continue the Excel example and balance the primary digester and eventually the whole AD plant. We start with the feedstock table as previously calculated. I collapsed the table to make some room on the slide. On the right side, we have a list of parameters that are required for the balance, starting with the kinetic constants of fraction 2 and 3. Remember, fraction 1 degrades instantly and no kinetics are required. Then comes the nitrogen content of biomass and the microbial yield coefficient YXS. Then the nitrogen mineralization degree, calculated as discussed earlier. All these parameters are required to model the fate of nitrogen in the digestion step. Next comes the TS of the solid and liquid digestate, then the solubilities of ash, organic nitrogen, total ammonia nitrogen, and the substrate fractions. We do not need a solubility for fraction 1 as it degrades completely and cannot be found in the inflow of the separation step. We choose a solubility of 50% for the medium-fast degradable fraction and of 20% for the slowly degradable fraction, which consists mostly of insoluble particles. And lastly, we have the sizes of the primary and secondary digester and their maximal TS content. We start with copying the feedstock properties into the first row of the balance and calculating the dry matter and organic dry matter flows. The substrate mass flows, denoted by a capital S, are the mass of biogas times 1 minus the hydrolysis water content times the respective fraction percentage. The mass flow of substrate fraction 1 is 0.38 tons per day. The substrate concentration, denoted with a small s, is the substrate mass flow divided by the fresh matter mass flow. We repeat the exercise for fraction 2 and 3. To calculate the biogas production, we no longer simply use the fixed biogas yield. We will need information about the digester sizes, the dilution requirement, ultimately about the residence time in each digestion step. The residence times depend on the dry matter degradation and dilution requirements. They can only be calculated iteratively. So, we need the estimate of the residence times, then calculate the conversion efficiencies, and with that the mass balance. The mass balance will give us the effluent streams of each digester stage, which can be used to calculate the residence time. We then update the residence time estimate and repeat the exercise. I will walk you through. As first estimate for the residence time of the primary digester, we use the input-related residence time, reactor mass divided by inlet mass flow. We have no information about the size of the effluent stream of the primary digester, so we use the same stream to calculate the residence time of the secondary digester. Now we calculate the steady-state substrate conversion rate for each substrate fraction in each digester. For fraction 1, it is 100% as per definition. Fraction 1 converts to biogas instantly and completely when added to a digester. For fraction 2, we use the steady-state solution of the CSTR. Eta is 1 minus 1 over 1 plus k tau, the Damköhler number. We pick the correct reaction constant and residence time for each substrate fraction in each digester stage. Then we calculate the total conversion of each substrate fraction in the reactor cascade. It is the conversion in the first stage plus the remainder, i.e. 1 minus the conversion in the first stage, times the conversion in the second stage. Lastly, we calculate the total conversion by multiplying the conversion efficiency of each fraction with the percentage of the fraction in the feedstock mix and add up the results. Fraction 1 converts completely, fraction 2 converts to 99.6%, and fraction 3 converts to 93%. The total conversion efficiency of the plant is 96.2%. The substrate mass flows in the biogas stream are simply the substrate flows in the feedstock times the respective substrate conversion efficiency. For substrate fraction 1, 0.38 tons per day are in the feedstock, the conversion is 100%, so 0.38 tons per day will be in the biogas. We repeat the exercise for fraction 2. And 3. The organic dry matter flow of the biogas is simply the sum of the 3 substrate mass flows. The loss on ignition of biogas is defined as 100%. The dry matter flow is the same as the organic dry matter flow. The TS of biogas is defined as 1 minus hydrolysis water demand. We can calculate the biogas fresh matter stream by dividing the dry matter flow with the TS of biogas. We then quickly balance nitrogen, as in the examples before, and calculate the concentrations of all species. Then we balance the average digestate by subtracting biogas from the feedstock and calculate its properties. Next, we calculate the split of solid and liquid digestate. We start with the rule of levers to calculate the amount of solid digestate produced. Then we use the solubilities to calculate the LOI, organic nitrogen and total ammonia nitrogen of the solid digestate, as shown in the previous episode of this mini-series. We use the same solubility concept to calculate the concentration of the respective substrate fractions in the solid digestate. Remember, substrate is fresh matter soluble. Then we calculate all mass flows in the solid digestate from the fresh matter flow and its composition. Lastly, we balance the liquid digestate mass flows and calculate its composition. We can check the balance by adding and subtracting all in and outgoing mass flows for each species. It should add up to 0. The balance around the whole AD plant gave us a second data point that is required in the iteration: the composition of the process water that is recirculated back into the digester stages for dilution. It has the same composition as the liquid digestate. This process water still contains substrate, which will be converted to biogas in the digesters. This makes the process water composition part of the iteration loop. We write the results of the first iteration into a line. From now on, we balance the primary and secondary digester stage individually. The balance around the whole plant is only required in the first iteration loop. The inlet flow to the primary digester is the feedstock. We know its mass flow and composition. We also know the current estimate of the composition of the process water going into the primary digester. Normally, we would now calculate the biogas production and average digestate, and then use the dilution rule of levers to calculate the process water required for dilution to the target TS. But now the process water does contain substrate, meaning that its TS will decrease slightly in the digester as some of its dry matter will be converted to biogas. The formula for the required process water dilution becomes slightly more complicated. It depends on the TS of the feedstock, the process water before its substrate has been digested, the biogas, and the target TS in the digester, here 12%. Further, it depends on the substrate concentrations in the feedstock and the process water and the respective substrate conversion factors. The required process water mass flow is 53.4 tons per day in this example. Now that we know the fresh matter flow of process water, we can calculate all other mass flows with its composition. We calculate the biogas mass flow from the substrate mass flows. The substrate mass flow in the biogas is the sum of the respective substrate in the feedstock and process water times the substrate conversion efficiency. Then we add up the substrate flows of the biogas to get its organic dry matter flow. With its known LOI and TS, we can calculate the dry matter and fresh matter flow of biogas. In the nitrogen balance, we multiply the nitrogen mineralization term with the substrate conversion efficiency of the primary digester. We balance total ammonia nitrogen as previously. Now we can calculate the biogas composition. Then we can balance the effluent of the primary. It is feedstock plus process water minus biogas. And finally, we can calculate the effluent properties. The total solids of the primary is 12%. The formula for process water dilution works. Next, we balance the secondary digester in the same way. Here is the nitrogen balance of the secondary digester. We apply the conversion factor of the secondary digester and the nitrogen mineralization degree to the residual organic nitrogen load coming from the primary digester. The rest of the secondary digester is balanced like the primary. We can now have a look at the whole balance. The first rows show the estimate table. We have previously estimated the hydraulic residence times of the primary and secondary digester and the process water composition. Based on those estimates, we calculate the mass balance for the primary and secondary digester, for the separation and around the process water tank which deals with the process water distribution. I want to direct your attention to the highlighted cells. With the mass balance, we have calculated the digester effluent streams, which are used to calculate the hydraulic residence times of the primary and secondary digester. In the initial estimate, the residence times were 43.5 and 34.8 days. We can write the updated hydraulic residence times on the left side of the table labeled HRT real. After the first iteration, the residence times dropped to 33.4 and 19.5 days. This is because substantial ingoing dilution streams to both stages, which are far higher than the outgoing biogas mass flows. We can calculate the relative error of the residence time estimation. Now I simply copy the body of the calculation 10 times below each other, making sure to use correct absolute and relative references. The next screenshot shows the table for the first iteration. The iteration number is shown in the upper left cell. I simply scroll down in the Excel sheet. The residence times are updated again, from 33.4 to 31.3 days for the primary and 19.5 to 18.1 days in the secondary digester. The error is only 6 and 8% after one iteration. We can also compare the new process water composition to the old values. The errors are quite large to begin with. The largest error is 84% for substrate fraction 2. We repeat the iteration. After iteration 2, the error in hydraulic residence time is less than 1%, and the errors in the process water compositions drop as well. The error in the substrate 2 composition is now 49%. After iteration 3, the residence time error is less than 0.5%, and the largest error in the process water composition is 13%. Iteration 4 takes the residence time error to less than 0.1% and the process water composition error to less than 2%. After 10 iterations, the errors in the residence times are 0, and the maximal error in the process water composition is less than 0.03%. At this point, we have reached machine precision, and the model error is much larger than the balancing error. The solution is good enough. The final residence times are 31.1 days for the primary and 18.2 days for the secondary digester. Now that we have a working kinetic model, let's make some sensitivity analyses. First, let's vary the size of the primary digester. This figure contains many lines. I will explain them in detail. The abscissa shows the primary digester size. On the left ordinate, we plot the residence time of the primary and secondary digester. This is the blue line for the primary and the orange line for the secondary digester. In our previous example, the primary digester had a size of 5,000 tons and a residence time of 31.1 days. When we vary the digester size, the residence time changes accordingly. At the first glance, the correlation looks linear, but the correlation is slightly convex. This is because the dilution requirement increases when the digester size shrinks. The orange line is the residence time of the secondary digester. It increases slightly with larger primary digester size because of the higher conversion in the primary and lower dilution requirement in the secondary digester. The right ordinate shows the conversion efficiency of the primary digester and the total conversion efficiency from 0 to 100%. The green line is the conversion efficiency of the primary digester, and the light blue line is the conversion efficiency of the total plant. In fermentations where the hydrolysis step is rate limiting and the diet contains a high concentration of fibers and inert organic dry matter, the ability to handle high viscosities, i.e. high TS concentrations in the primary digester, is equivalent to the digester size. This is because the dilution stream required to bring down the digester TS to its target level. If the plant uses less dilution, it can provide the same residence time with smaller digester volumes. As a result, the organic loading rate goes up, but the residence time stays constant. I discuss residence time, organic loading rate, and how the organic loading rate is no design criterion for CSTR biogas reactors without biomass retention in my biogas myth presentation. Here is the same plot for the TS in the primary digester. It shows a very similar behavior to changing the primary digester size. Most notably, the residence time curves show two kinks. Let's start with the blue line of the primary digester. In previous examples, the primary had to be diluted to 12% TS and had a residence time of 31.1 days. If we lower the maximal TS in the primary, more dilution is required and the residence time drops. If we improve the mixing technology in the primary digester so that we can handle higher viscosities and TS in the primary, the dilution requirements drops and the residence time increases. At around 15.8% TS in the primary digester, we reach the TS of the average digestate and no dilution is required at this point. Increasing the maximal TS further will not lead to a higher residence time. The dilution is already 0. The effect is similar for the secondary digester, which can handle up to 9% TS. At 12% TS in the primary digester and 9% TS in the secondary, both the primary and the secondary digester must be diluted. For the dilution of the secondary, it does not play a role whether the dilution flow is added to the primary or the secondary. If we increase the maximal TS in the primary, the secondary will still need the same amount of dilution. Every ton of dilution saved in the primary must be added to the secondary digester to dilute it to 9%. The curve is not completely flat. There is a slight effect based on lower dilution required for the secondary due to the higher dry matter conversion of the primary at higher residence times. Only if we dilute the primary digester to around 10.2% total solids, the dilution requirement of the secondary digester drops to 0. The difference from the 10.2% TS at the inlet to the 9% at the outlet of the secondary digester stems purely from the dry matter conversion to biogas. If we dilute the primary digester further, the residence time in the secondary digester is also affected. We can see the equivalence of digester size and maximal TS in this scenario when viscosity dilution is required. I could have scaled the two figures so that the curves would overlap exactly. In this example, the hydrolysis of the feedstock mix is the rate limiting factor of the plant. Almost half of the substrate is the slowly degradable lignocellulose fraction. Before I finish the presentation, I want to discuss what happens if we increase the feed rate further. Similar to the last two slides, this plot shows the hydraulic residence times and the conversion factors as a function of the daily feed amount. In addition, The plot also shows the dilution process water demand, in purple for the primary and in green for the secondary. In the previous example, the daily feed was 115 tons per day, or 100% in the upper abscissa, and the residence time was 31.1 days. If we increase the feed rate by 20%, the residence time in the primary digester drops to 20 days, a drop by more than a third. If we feed more and increase the feeding to 140%, the residence time effectively halves. Without the effect of dilution, we would need to double the feed rate to half the residence time, but the dilution and the effect of reduced dry matter conversion at lower residence time makes this effect nonlinear. At 115 tons per day, we need around 60 tons per day dilution for the primary. But if we double the feed amount, the process water demand increases to more than 360 tons per day. And that is just for the primary digester. The secondary digester needs almost the same amount as well. The dilution stream quickly pushes the residence time in the primary digester down, to a point where the biocenosis becomes unstable and is washed from the digester. This death by dilution is common in plants that were either designed incorrectly or where the feedstock composition is retroactively changed in favor of feedstocks with lower organic dry matter specific biogas yields, i.e. cheaper feedstocks. The feedstock market prices easy digestible feedstocks with high dry matter specific gas yields higher, consciously or unconsciously. See my presentation about feedstock characterization about the interchangeability of feedstocks. The mass balance techniques shown here can be used to assess which feedstock can be fed into an existing plant or how to design a plant for a requested feedstock mix to prevent this behavior. When kinetics are taken into account, biogas yields are no longer constant but depend on biogas potential and conversion rate. Conversion rates are calculated with degradation kinetics from hydraulic residence times, which are the mass of digestate in the reactor divided by the reactor effluent stream. The mass balance becomes nonlinear and requires iterative calculations to solve. The residence time depends on the conversion rate, and the conversion rate depends on the residence time. We defined a new species, the substrate. Substrate plus water reacts to biogas and biomass. The extent of this reaction is the conversion factor. We use 3 different substrate fractions, the rapidly, medium-fast, and slowly degradable fractions, each with different kinetic constants. We defined the concept of solubility to model the separation step and a new rule to calculate the process water demand for viscosity dilution, which takes into account that process water itself will be partly converted in the biogas reactor. I showed a simple algorithm to balance the AD plant and solve the mass balance for this nonlinear case. First, we estimate the hydraulic residence time for every digester step and the process water composition. And then we calculate the mass balance from which we extract new, updated hydraulic residence times and the process water composition. We repeat the exercise a couple of times until the mass balance no longer changes. I showed an Excel example of the full mass balance. It contains all formulae that are required to duplicate the mass balance. The Excel model allowed us to make some parameter studies. We showed that for an AD plant requiring dilution in the primary digester, the ability of the primary digester to work at elevated TS is equivalent to the digester size of the primary digester. We also investigated what happens if we push up the feed rate, and the plant suffers death by dilution. This concludes a 3-part mini-series about the mass balance of a biogas plant. The ability to mass balance a biogas plant correctly is absolutely crucial in every AD project. I hope you learned something new and are now able to duplicate mass balance calculations in Excel. I see you in the next episode of Biogas Basics.